Okay, so we are going to continue our example from last time, example 10.15, and we are on part C. And the question states, what is the total linear momentum before and after the collision? So remember that linear momentum equals mass times velocity. Okay, so in our initial state, this is just going to be our mass of the first object times our velocity initially. Okay, so that's going to be 0.05 kilograms times our velocity, which was 30 meters per second, I believe. Let me double check that. Yes. Okay, so we can go ahead and get that. And that gives me 1.5 kilograms meters per second. So this is my initial linear momentum. And then after the collision, P prime, it's going to be a little bit different because now we have two objects. So we have the linear momentum of the first object and the linear momentum of the second object. Okay, so this is going to be our mass times our velocity. Okay, our final velocity, I should say, plus our second mass times our velocity. But our velocity is going to be a little bit different since now we're looking at a stick. Okay, so it's actually going to be the velocity of the center of mass of that stick. Okay, now our center of mass is calculated as the final, I should say just V prime, as our final V prime divided by 2. Okay, so this is going to be my center of mass velocity, linear velocity. All right, so we can go ahead and simplify this as m plus larger m, or m1 plus m2, times v prime, and this should be divided by 2 if I plug that in correctly. And remember that our v prime, or v, can be related to omega. Okay, so omega prime, I should say, times r. Let me double check that that is correct. Oops. Yeah, v equals r omega, so we're good. Okay, so I'm going to go ahead and now plug that in here. Okay, so this is going to be omega prime times r. So my first mass is 0.05 kilograms. My second mass, I believe, was 2 kilograms. Yes, 2 kilograms. And we're going to divide that by 2. And this is going to multiply by our final angular moment, or angular velocity, which is 1.74 radians per second, and times our radius, which is 1.2 meters. 1.2 meters. Okay? So you can plug everything into your calculator, and you'll get your momentum, is 2.19 kilograms meters per second. So again, this is the momentum after the collision, the linear momentum. Okay? All right, so let me go back to our PowerPoint here and just give you guys a tiny bit more information of angular momentum. So angular momentum does have a vector aspect, okay? So when we write down our L, it should be some kind of vector as well, okay? And that's because it is based on our angular momentum, omega, which also has a vector quantity, okay? Or is a vector quantity. And the way we learn how, kind of how to describe that motion, the direction of motion of the vectors, is through this thing called the right-hand rule, okay? So, without getting into, I guess, too much detail, just to kind of describe it to you guys, the right-hand rule is, first of all, super useful for this. And let's go ahead and kind of go through some examples. So if you stick out your hand in a straight line, so I'm really bad at drawing hands, but if you have your hand, right, you got your thumb, that's not a thumb. Okay, you got your hand and your thumb and your fingers. Okay, so you just got them like out straight, your right hand, okay, and you curl your fingers inward, just like this is showing you here. Your thumb will point in the direction of your angular velocity as well as your angular momentum, okay? So again, your thumb is going to point in your motion of the angular velocity and your angular momentum, and your hands are curling in the direction of rotation, okay? So if we're looking at this disc is rotating counterclockwise, okay? So your momentum and your angular velocity is going to be pointing up in this case, okay? So using your right hand, you can show this, okay? Now I've got a couple more examples here, but don't, worry too much. I just want you guys to understand, kind of trying to figure out that direction, okay? So we've got our direction of motion here, or direction of rotation, again going counterclockwise, and you can see that our angular momentum is going to be in this direction here, okay? It's a little off from the axis if we claim that this is the axis, but, this is going to be your direction. Now, again, looking at another one, this merry-go-round, okay, you can see there's a torque involved, there is an angular velocity and an angular momentum, and again, using the right-hand rule, you can tell which direction those three are pointing, okay? So I just wanted to show you guys a few of these examples here to kind of understand the right-hand rule and how it's useful in these cases, okay? All right, so that is the end of lecture. I know that one was kind of long. I had a lot of examples for you guys, but I think they'll be super helpful in doing your assignments. And I will be putting those up sometime this week. So let me know if you guys have any questions. Feel free to email me.